Hello everybody, Assalamu alaikum, and welcome to Study Bee. Oops, Astro Bee. I changed the name of my channel and I forgot. Anyways, today I'm very low on energy. I had a very long day, so I'm going to try to push an hour and see what we can get done. My goal for today is to cover the notes for forces and do at least 15 fast paper problems. Okay, so let's get started. Bismillah, and you guys can do it, okay? In the name of God, we're starting the lesson, hoping that His mercy makes it easy for us and that by the end of the lesson, we have learned something new. Okay, sorry. Okay, so what's a force? I'm going to try to rush through the notes, okay? So I'm sorry if you needed more clarification with something. As I've said earlier, I will try my best to come up with detailed lectures within a few months. A force, we've been studying it ever since, is a push or a pull. A force can do different things. It can make a stationary object move. If you have a box on a table and you push it, the box will start moving and then come to a halt after a while. And it stops moving because there's a counter force, friction, that tries to stop the moving object. We'll discuss friction in a while. So a force can cause a stationary object to move, and if something's already moving and you push it, it's going to speed up. So force is capable of changing the speed of moving objects. Like if you apply a push in the direction of motion, it's going to speed the object up. And if you apply a force opposite to the direction of motion, it's going to slow the object down. And if you apply a force at a certain angle to the object, you can also change the direction of the moving object. And if you happen to drop a very, very heavy weight, which is a type of a force on an object, you can deform it, right? It's not Tom and Jerry where after deformation you come back to your original shape. This is real life, where once a spring or anything is deformed, it doesn't go back to its original shape. Okay, so if you hang a weight from a spring, it's going to stretch. Okay, and when you let go of it, it's going to compress, or no, not compress, go back to its original position. And if you have a spring and you apply force from both sides of the spring, you will compress it. And if you hang a very, very heavy mass from this end of the spring, you will likely deform it such that when you remove the weight, it won't go back to its original length. And I'm sure you guys have done that as kids because I did that all the time with whenever the um, would ballpoint pens would run out of ink. I'm not sure if you guys have used ballpoint pens, but it was a huge thing when I was doing my A levels and IGCSEs. Yeah, I didn't use ballpoints in IGCSEs. I used them in A levels because I just wanted to write really fast. And when I was in IGCSEs, I was a very tidy kid, so I wanted my handwriting to be pretty. I wanted my notebooks to look pretty, but in A levels, I didn't give a crap. But I got the grades, guys. I got the grades, so we're good, okay? Yeah, so there's two types of forces. We have contact forces, we have non-contact forces. Contact forces are forces that are applied when two surfaces are in contact. Like rub your hands together, you're going to feel some warmth. That warmth or heat is a product of friction. When you have two surfaces in contact rubbing against one another, friction produces heat. Okay? Then we have air resistance. It's a type of friction. It's a friction in the air, okay? And imagine that you're walking on the road, okay? You're just walking, nothing like not much, just walking, and you will feel a little bit of air against your body, right? But when you start running, you will feel more air against your body, right? The faster you run, the more air you feel against your body. That is air resistance. What is resistance or friction? Friction is an opposing force. It tries to stop moving objects, okay? If it's in solids, we call it friction. If it's in gases, we call it air resistance. Like if you're moving through the air will try to stop you. It's an opposing force. It's air resistance. It's friction in the air, okay? Now, non-contact forces are forces that do not need two objects to be in contact for them to act. I loved magnets when I was a kid. I mean, I love magnets still. Uh, yeah, now it's just that as a kid, I used to use magnets to play with them. Now I use magnets for my job. So, yeah. Anyways, I'm sorry. I think I should record lectures in the morning because by the evening I'm so done with everything that my brain's all over the place, and then I have all of these stories coming to my mind when I just literally decided to finish a lot of stuff in an hour. Okay, no more yapping, no more talking, we're gonna get back to work. Okay, yes, we're determined. Yeah. So when you recall a time when you were playing with magnets, okay? And you would have noticed that you didn't necessarily need to touch the magnets for them to attach to one another. When they were like a little distance still far from one another, they would snap together and like attach to one another, right? So this is a non-contact force. It acts um, at a certain distance as well. Okay, so let's look at it in a little bit more detail. So basically, if you have this magnet, it has a certain area around itself, okay, in which it attracts things to itself. Okay, so unlike poles, north and south attract. We know that. So if you have your magnet anywhere over here, nothing's gonna happen. But if you bring the magnets close enough that these circles interact, the magnet's going to snap and attach with the North Pole, okay? So this circle is basically the magnetic field. It's the area around the magnet in which the attractive magnetic force can act, okay? Outside of the circle, the magnetic force is not going to act. And we have unlike poles, south and south, or we could have had north and north. Unlike poles, sorry, like poles repel. Okay, so if you have these like poles and you bring them close enough, they're going to repel. You're never going to be able to touch them together. I tried a lot. Trust me, I spent hours trying to do that. As a kid, I could never do that. So yeah, this works. Physics works. Okay. We have a few type of forces. We have tension. Tension is a force in stretchable objects like strings and ropes and springs. Okay, when something is not stretched, the tension in that object is zero. When you stretch something, you are creating tension in that object, and tension is always away from point of observation. Okay, so if this is your point of observation, tension is going to be away, and it's going to be away from here as well. Then you have normal contact force. It's a force that a surface exerts on an object that's resting on it, and it's always perpendicular to your surface, okay? So if you have a table and you have a book or a box resting on the table is going to apply a force perpendicular to itself that is called a normal reaction force. And it's not upwards, okay? There's a difference between upwards and perpendicular. Weight is always downwards. It doesn't matter if the surface is sloped, slanted, straight, or whatever. It's always going to be downwards. However, normal reaction force is always perpendicular to the surface. So this is your surface. You're going to draw a line that is at 90 degrees to your surface. So this is your normal contact force. Next, upthrust. You might have noticed that when you throw something in the pool or any water body, it floats. Not everything floats, but a few things float, right? We're going to discuss why some things float and some sink anytime soon as well. But for now, look at this example. Basically, water is applying an up thrust force on the object, okay? It's a force exerted by fluids or liquids when you submerge them in a liquid, okay? So if you submerge any object in a liquid, the liquid's going to exert an upward force on it, okay? And that force is called upthrust force, and it's equal to the amount of volume of the liquid that's displaced by your object. And it's upwards because it's from high to low pressure. And at the bottom you have high pressure, at the top you have low pressure, so it's from bottom to top. So you have an up thrust force upwards from the water body. So if the upthrust force is more than, it can never be more than the weight of the object because it's kind of related to how much space it's displacing, right? Of the volume of the, sorry, space of the liquid. So if your upthrust force is equal to the weight of the object, it's going to float. But if the upthrust force is less and the weight is more, of course, if the downward force is more, the object's going to sink. We will discuss this when we're talking about density as well in a little bit more detail, but for now, I think this is enough. If the upthrust is equal to weight, it's going to float. If upthrust is less than weight, it's going to sink. Okay, and it intuitively makes sense as well. If the weight, which is the downward force, is more, the object's definitely going to sink, right? We discussed friction a little bit. Let's look at it a bit more. Friction is an opposing force. It opposes or resists motion. So wherever you see motion, there's going to be friction. Wherever you see a moving object, there's going to be a force that's going to try to stop it. So if the object is moving forward, friction is going to be backward. Friction's always in the opposite direction to the direction of motion. Okay, energy is transferred in the form of heat when there's friction. Now, why does friction exist in solids? Let's look at that. So basically, the surfaces that you see are not perfect. There's imperfections or grooves in the surfaces, okay? And when you have an object that is, let's say, sliding on a table, the grooves of the object in the table are going to interact and it's going to stop the object from moving, okay? And in fluids and liquids, particles bump into the object that's moving, and we also call it drag force, okay? Wonderful. So, free body diagrams. You need to know how to draw free body diagrams. A force is a vector quantity, okay? And when we're talking, oh, wait, hold on a second. I just realized I say okay a lot. I just took 5 seconds to contemplate on that, and I'm gonna try not to say so many okays. Okay? Oh no, I said it again. I'm not gonna try it. Okay, no. Damn it. Guys, usually I edit all of this out. Do I want to add it to that? Yes, totally. Do I have time to do that? Hell no. So please, here are the raw, unfiltered videos of me trying to explain lectures and forcing myself to come back to my teacher mode. For those of you who've had tuition with me, I'm sorry. This is very hard to do when I'm by myself and recording. When you guys are around in the lessons or lectures, I'm more human. Okay, no more talking anymore. Go back to work. Yes. So a force is a vector quantity. Whenever we're talking about vector quantities, we are lazy people. We want easier ways to demonstrate them. Okay? So, yeah, it's okay. You can say okay, right? I was saying that to myself. Don't worry. Yeah, if you want to count how many times I'm going to say okay, go ahead. I'm dead sure it's going to be at least 50 times by the end of the video. Anyways, yeah, so I was saying that when you have a vector quantity, it has two things. It has a size and direction. You want a smarter way to demonstrate that, so we came up with arrows. The length of the arrow is going to tell you how big or small the quantity is. It's going to tell you the size, and the direction of the arrowhead is going to tell you the direction of the vector quantity. Okay, so, if you have a mass hanging from the spring, oh yeah, so we were discussing free body diagrams. Free body diagrams are just smart ways to demonstrate your situation. It's very helpful because you draw a really, really little diagram that has arrows in it, and the arrows are depicting forces or any vector quantity. So if you have an object, there's the downward force weight acting on the object. Tension is acting up, it's always away from the point of observation. We learned that. So this free body diagram is going to help you find net forces and a lot of important stuff. So let's draw a free body diagram for a parachutist falling down. This is your parachutist, and she has her weight acting down, and she has an opposite force, which is air resistance. A box sliding down a slope. Weight always down, normal reaction force perpendicular to the surface. And if the box is sliding down, then friction is going to be opposite to the motion, okay? So it's backwards. A car accelerating along a road. If it's accelerating, it means the forward force is more than friction. So the thrust, which is the forward force, is bigger. That's why this arrow is larger than the yellow arrow that's showing you friction. Then the object is not moving up or down, so that means the weight and normal force are equal. So this is our cutesy free body diagram for a car accelerating along a road. Anyways, so how do we find net forces? First of all, what is a net force? A net force is a single force that describes the combined effects of all of the forces on an object. Okay? Imagine you have a box of candy and there's and you're okay, so imagine you brought a oh got a text message. Who is it? My dad's calling. No. What do I do? I don't want to filter the video. I can't even take a call. Let me text him. Okay. I think he called my sister, so that should be okay, but I dropped a message. I really miss him. I want to take the call, but I'm too lazy to edit all of this out. No worries. Yeah. So, oh, how much do we have left? We have a. No, I'm not crying. I'm okay. Yeah, so I'm just gonna try to rush through it. I know I've been saying that, but oh no! There's a spider in my room. Wait, I think it was in the other corner. How did it get to the other side? Poor spider. I'm in a meeting, don't talk. Not a meeting, I'm recording a lecture and I'm not gonna edit this out. Sorry guys, my sister came and she's gone. I didn't want her to yell or say something stupid. Back to work. No, not back to work yet. I got another message. Please, just skip and move on, guys. Oh, my dad liked the message. I'm so glad he didn't give it a thumbs up and hearted the message. That's cute. You know how dads always give a thumbs up to every single message? Like it doesn't matter how serious or emotional or whatever it is, he's always gonna be like, thumbs up, you're good. But no, this time he often likes like hearts my messages, so I shouldn't be complaining. A resultant force is a single force that will give you a combined effect of all of the forces that are acting on that object, okay? So if you have a box and there's one person pulling it to the right and another person pulling it to the left and another person pulling it down and like that, of course the box is not going to move into all directions until it breaks and every person gets a piece. If you want the box to be in one whole form piece, then it's going to go in any one of those directions based off of who's applying the biggest force. So that one direction in which the box will move is going to be your net force. Okay? How do we find net forces? If you have parallel forces, and if they parallel forces are basically forces that are in the same axes. Like if you were to draw a line, they would all be in the same line, okay? So if you have anti-parallel forces, which are in opposite directions to one another, you're going to subtract them. You have 5 newtons here, 5 newtons here, 5 minus 5 is just 0. So the net force here is 0. Your object is stationary. There is no net force on it. There's equal amounts of forces on both sides, so the object is not going to move. That's an example of a balanced force. On the other hand, if you have 8 newtons to the right, 5 to the left, 8 take away 5 is 3 newtons, and 8 newtons is bigger, so the net force is going to be 3 newtons to the right. And if you have both forces in the same direction, you will add them, and the net force is, of course, to the right. So remember, opposite directions you subtract and same direction you add, and the bigger the direction of the net force is going to be in the direction of your bigger force. All good? Next, laws of motion. You have three laws of motion. The first law just literally says if an object is at rest, it's not going to move. Okay? If you have what do I have? If I have my sunscreen on the table, it's not going to move until I push it or, just like I don't know, try to move it. It's just going to stay there. So basically, first law is very, very, very much common sense. Okay, I don't know why even this is in the syllabus. Actually, I do know why this is in the syllabus. I shouldn't be saying that as an astrophysics specialist. But at IGCSEs, this is very simple. Second law just says that the more force you apply, the more the object is going to accelerate. Okay, so it just says that the acceleration is proportional to the force that you're applying and it's inversely proportional to the object's mass. It's just saying that heavier objects will accelerate less if you apply the same amount of force, and it's just saying that same massed objects, if you apply a bigger force, will cause bigger acceleration. Just if there was one thing you wanted to remember here, it would just be that force is directly proportional to acceleration and that F equals ma. Please just pause and read the rest of the stuff. The third law just says that if you apply an action force, there's going to be a reaction force. Okay, for example, if you throw a ball at the wall, you're applying an action force, there's going to be a reaction force. So the ball's going to apply a force on the ball, and that's what causes the ball to come back to you. The action-reaction forces, like this pair, is equal in magnitude but opposite in direction. So if you're applying 4 newtons to the wall's also going to apply 4 newtons to the ball, but the direction is opposite. That's why you are able to catch it back and play catch. Next, Hooke's law. Hooke's law just says that force is proportional to extension of the spring. If you have a spring, let's look at this to understand Hooke's law. If you have a spring, this is your unstretched spring. You hang a mass here, the spring's going to stretch. So this was the original length, and this is the stretched length. The change in length is called delta x, or extension. Now, if you were to hang a heavier mass, the extension is going to be more than the lighter mass, right? So big mass causes bigger extension. And what does mass have to do with this? This mass is causing a downward force, which is the weight. So basically, a bigger force causes bigger extension. That is Hooke's law. Pretty cute. So Hooke's law says that force is proportional to extension. And in math, you should have learned that when you remove this proportionality sign, it introduces an equal sign and a constant. And in this case, our constant is a spring constant, K. You have a force extension graph, and the gradient of this graph gives you K, spring constant. And the part where your graph is a straight line, that is the part that's obeying Hooke's law. That part is saying that force is proportional to extension. But look at this now. Now, if you were to hang like 10 times the mass that you were hanging earlier, the spring's going to stretch a lot, okay? And it's going to be deformed. What does deform mean? It means that when you remove the mass, it's not going to go back to its original position. Maybe it will go back to this length, right? So the spring has been deformed. So beyond this point, it becomes really, really easy to stretch the spring further. So this is your limit of proportionality. This is where the spring has deformed. If you were to look at it in a graph, and beyond this point, it's easier to stretch the spring and it becomes a curved graph. Now, the last part, oh my god, we're almost to the end. Yay! Alhamdulillah. Okay, so the circular motion. Circular motion is very, very cute and simple. It just says that if you have an object, okay, and it's moving in a certain direction and you apply a force perpendicular to the object's motion, it's going to move in a circle. That is it, guys. That is it. If you have an object moving in a certain direction with velocity v and you apply a perpendicular force on it, the object's going to curve its path and move in a circle. Of course, if the force is no longer perpendicular to the object's velocity, it won't continue to move in a circle. As long as the force and velocity are perpendicular to one another, the object's going to be in circular motion. Now remember that the magnitude of the velocity could be 200 meters per second throughout the circle. Okay? The magnitude of the velocity can be 200 meters per second throughout the circle. So it might look like velocity isn't changing. But what is velocity? It's a vector quantity. It has a magnitude and direction. If I say this object is moving in a circle at 200 meters per second, is the velocity changing? You will say yes, it's changing because the magnitude 200 meters per second is the same, but the direction is changing at every constant. And in a vector quantity, we don't just care about magnitude, we care about direction as well. So yes, if an object is moving at 200 meters per second in a circle, its velocity is changing because its direction is changing. And if its velocity is changing, it is accelerating. It might look like it's not speeding up, but its direction is changing. So its acceleration is changing. And what's the direction of the acceleration? Acceleration is in the same direction as your net force. Your net force in a circle is towards the center of the circle, so your acceleration is also towards the center of the circle. I'm so sure if you haven't heard of these things before, it might be a lot to take in at once, but these are all the main points that you should know for your exam. Take a take a pause, like pause the video and look at it in a little bit more detail. Okay, yeah, I think we're done with the notes. Let me see if we want to do more. I don't think so. Yeah, I don't think so. We'll see that in our next class. If there's any questions about moments, we'll come back to the notes and continue, I guess. How much time do I have left? By the way, these notes are from Save My Exams. Amazing, wonderful website, guys. Please make use of it. Okay, not notes, sorry, I meant past papers. Let's do this. A man pulls a sledge. We have 20 minutes, right? Oh my god. I'm gonna try to do at least 10 questions, guys. A man pulled a sledge of mass 25 kilograms. Oops, what is happening? Okay, it's working now. Yeah, that's good. A man pulls a sledge of mass 25 kilograms across level ground with a horizontal force of 60 newtons. Okay, so there's a mass, M. Please draw a diagram whenever possible. The mass is 25 kilograms, and a man pulls a sledge of mass 25 kilograms across level ground with a horizontal force of 60 newtons. So there's a horizontal force of 60 newtons. A man's pulling it. They don't tell you it's right or left, so you can choose your own directions. A constant force of friction of 20 newtons acts on the sledge. If the man is pulling to the right, what's the direction of friction? If the object is moving to the right, what is the direction of friction going to be? Opposite to that. Where in whatever direction an object is moving, friction is going to be opposite of that. So your friction is going to be to the left, and it's 20 newtons. I'm drawing a smaller arrow because it's less than 60. What is the acceleration of the sledge? So remember, F net equals ma. F equals ma is the most common formula. It's examiner's famous formula, or sorry, favorite formula. So you will, I can guarantee that you're gonna get a question, not just one question, multiple questions that involve F equals ma. So please, please, please remember it. So net force is equal to mass into acceleration. And remember, this is not just F, it's F net. It's your net force. So we just learned that if you have anti-parallel forces, you want to find the net force, you're going to subtract them. So your net force will be 60 take away 20. Oops, no. Yeah, 60 take away 20, 40. 60 take away 20 equals, what's your mass of the box? 25. And acceleration is what we're finding. 60 take away 20 is 40. Over 25. Why over 25? Because 25 is multiplying here. I take it to the other side and I divide it. And that is equal to your acceleration. That is 1.5. And the unit of acceleration is meters per second squared. So 1.6, sorry, not 5. 1.6 meters per second squared. Next, a car moves in a circle at a constant speed. What's the direction of the resultant force acting on the car? Remember, guys, resultant force is always towards the center of the circle. If this is the center of the circle turned by the car, the resultant is going to be towards the center, so it's speed. Four forces act at a point as shown. What is the size of the resultant force? Remember, guys, how do we find resultant force of anti-parallel forces or forces in opposite directions? We subtract. So up and down is the same, so they cancel out. 2 take away 2 is 0, so there is no net force in the vertical axes. In the horizontal axes, you have 8 newtons to the left and 4 newtons to the right. So it's going to be 8 take away 4, 4. So your net force is 4 newtons. Is it going to be to the right or the left? They haven't asked you that, but you should know. Yeah, it's going to be to the left because 8 newtons is your bigger force, so your net force is going to be in the direction of the bigger force. So 4 newtons to the left. When a car turns a corner at speed, it risks toppling over. Two factors affecting the stability of a car are height of its center of mass and the distance between its front wheels. Which factors make the car more stable? Let's go back to the notes and see where we have stability. Okay, so I have stability discussed here. Yeah, so yep, I'm just gonna cover this much for the question. So stability, no, actually I'm gonna have to start here, or let me see. Yeah, I'm gonna have to start here. So center of gravity of an object is a point at which the weight of the object may be considered to act. It's not like all of its mass is in the center, but it's the point where if you're pivoting at that point, the object will be balanced. You might have tried to balance a ruler on your finger, right? So when you put the finger or your hand in the middle of the ruler doesn't topple or it doesn't fall, right? So basically you put your hand at a point where you can consider the entire weight of the object to be acting. If that doesn't make sense, I'm sorry, I'll explain that in some other video. For now, remember how you find the center of gravity of an object. If you have a symmetric shape, like a regular shape, you draw lines from its vertices, and wherever the lines intersect, that's your center of gravity. You might think circle doesn't have any vertices or corners. You draw a line from any of its circumferences and any points on the circumference, and wherever the lines intersect, that is your center of mass. You do the same for these shapes. Now, stability. The wider the base, the more stable something's going to be. Think of this object, okay? So this is your object, it's standing upright here. Now, if I push it a little bit, what happens is that you have to look at the center of gravity of the object, okay? Center of gravity is in the center for all of these. So basically what I did was I took this and I did this, right? So I took it, I pushed it. Now the center of gravity is still falling within the baseline of my object. When your center of gravity goes outside the baseline, that is when your object is going to topple over. So the wider the base, the more chances there are for the center of gravity to lie within the baseline when you apply a push. So you see this object, even with the same amount of push as the object above, this object has a center of gravity still within the baseline, right? So this object is not going to fall, it's more stable. So what we learn here is the wider the base of an object, the more stable it's going to be. And the more mass there is at the bottom, the more stable it will be. So wherever there's more mass concentrated, center of gravity is closer to that point. So if there's more mass concentrated at the top of the waves, the center of gravity is going to be at the top. If there's more mass concentrated at the bottom, the center of gravity is going to be at the bottom. And the lower the center of gravity of an object, the more stable it is. So there's two conditions for stability. The first condition is wider base, and the second condition is lower center of gravity. Okay, now let's look at the question. What factors make the car the most stable? Center of mass has to be low, and distance between front wheels. So basically, it's saying if this is the wheel, this is the wheel, this is the car, The more the distance is between the front wheels, the wider the base is. Let's say that's your first example. Your second example is this. So if there's more distance between the front wheels, okay, the base is wider. So we want more distance between the front wheels. So it's going to be D. Okay, that's why your F1 cars are so low, right? Because they want the center of mass to be closer to the ground. Question number 5. A metal ball of mass 0.3 kilograms and weight 3 newtons is held so that it's below the surface of oil. It experiences an upward force of 0.3 newtons. When the ball is released, what's its initial acceleration? So you have a metal ball, its mass is 0.30 kilograms, and its weight is 3 newtons. Okay, so the weight of the ball is 3 newtons. And, okay, so basically this is literally just the F net equals ma formula, F equals ma. F net equals ma. So, what's your net force? 3 take away 0.3, because they're opposite forces, you're going to subtract them. Equals, what's the mass of the ball? The mass of the ball is 0.3 kilograms multiplied by your acceleration. You're finding acceleration. So 3 take away 0.3 is 2.7 equals 0.3 into acceleration. You're going to take 0.3 to the other side. It's multiplying with a here, so when it goes to the other side, it will be divided. So that would just be 9, I guess, meters per second squared. Okay. Yep, let's see question 6. Earth travels in a circular orbit around the sun at a constant speed. Which arrow shows the direction of the acceleration of the Earth and the direction of the velocity of the Earth? So remember that we learned that when an object is moving in a circle, its net force is towards the center. Remember that. Net force in a circular motion, in circular orbit, your net force is towards the center of the circle. And we know that F equals ma. This is just saying that force is proportional to acceleration. So whatever the direction of your net force is, that is the direction of the acceleration. So F net is towards the center, and acceleration is also towards the center. So net force and acceleration are both towards the center of the circle. So the direction of acceleration is going to be r, and velocity is q. Of course, it's moving in a circle, so velocity is going to be tangential to the circle. Now, what does that mean? It means that whatever point there is, you're going to draw a tangent. It's a straight line in the direction of the circle at that very instant, and the velocity is tangential to the circle. D. Question 7. Which object has the largest resultant force? Just find the resultant force in all of these. When they're in the same direction, you add them all. For this one, it's 15 newtons to the left. Here you have 30 newtons to the left, and 5 plus 5, 10 newtons to the right. So you have 30 newtons to the left and 10 newtons to the right. So your net force is going to be 30 take away 10, 20 newtons to the left. Here you have 20 newtons to the left and 30 newtons to the right. So your net force is going to be 10, let me write that in a different color, 10 newtons to the right. Here you have 20 to the left, 20 to the left, 10 to the right, so that's going to be 10 newtons to the right. So your correct answer is C. In which example does friction act in the direction of forward motion of the object on which it acts? In which example? My eyes are shutting down, guys. What time is it? 9:51. We still have 10 minutes. What question was I on? Question 8. In which example does friction act in the direction of forward motion of the object on which it acts? In a suitcase accelerating on a conveyor belt? No. On sandpaper rubbing in a wooden block? No. On the skis of a skier accelerating downhill on a smooth snow? Yes. C. So skis on snow, friction acts in direction of motion. Just remember that. And if you can't remember it, look at the other options and you'll be able to shortlist your answer. Tires of a braking car, we know that tires move you forward, so friction's backwards. So it's because when you're braking, like when you're applying brakes, the friction is what's causing you to stop, right? So it has to be opposite to the direction of motion, only then would it be able to stop you. Sandpaper rubbing a wooden block. Wooden block. When you are rubbing sandpaper on a wooden block, the wooden block tears, right? It wears off. Why is it wearing off? Because friction is opposite to that rubbing, and it's causing it to corrode, kind of. A suitcase accelerating on a conveyor belt. So if you have a conveyor belt and you have a suitcase accelerating on it, that there is still friction, guys. As on the skis of skier accelerating down on a smooth snow. When there is smooth snow, that is when friction is not as strong. So it's in the forward direction. I'm sorry, I'm distracted a little bit. Mm, yep. The diagram represents the moon on its orbit around the Earth, which arrow represents the direction of the resultant force. You guys know it. Circular motion. It's going to be towards the center of the circle. A. I love these questions. They're so sweet and innocent. An apple of mass 0.15 kilograms and weight 1.9 newtons falls from a tree. At one point during its fall, air resistance on the apple is 0.6 newtons upwards. What's the acceleration of the apple at that point? For apple, it has a weight of 1.9, 1.5 newtons, and air resistance is zero point 0.6 newtons. Okay, and you want acceleration, so we're going to do the same thing we've been doing since the beginning. F equals ma. F net is your net force. They're opposite forces, so you're going to subtract them. So 1.5 take away 0.6 is equal to mass of the object 0.15 multiplied by acceleration is what you're finding. So 1.5 take away 0.6, 0.9. This is such simple math that I'm using calculator for. Imagine, guys. This is how tired I am. That is just 6 meters per second squared. B. What time is it? We still have about 6 minutes, so why not do 5 more questions? 4 of the gravitational forces that act between bodies in the solar system are described below. Which two forces are Newton's third law of pair, action and reaction? Remember, guys, action and reaction forces have to be the same type of forces. So if you have weight, the other one has to be weight as well. So, force on the moon due to Earth. So wait, we're going to draw, so we have 3 things. We have moon, Earth, and sun. So this is our sun. Wait. So same type. This is what you're going to remember. So if you have the sun here, you have the Earth here, and you have the moon here. Don't come haunting me that I drew Earth and sun the same size. Yeah, so force on the moon due to Earth. So on the moon due to Earth. So that is the force on the moon due to Earth, which is the attraction of Earth. Earth attracts the moon towards itself, so that's the force on the moon due to Earth. Then the force on the Earth due to sun. On the Earth due to sun. So the sun attracts the Earth. So of course these two are not pairs. Force on the Earth due to moon. So moon also attracts the Earth towards itself. On the Earth due to moon. So of course it's this and this. P and R. There you go, because they're the same type of forces and they're anti-parallel. So they're going to be the same magnitude but opposite direction. A man pushes a heavy box along the ground. Force acts between the man's hands and the box. Another force acts between the man's feet and the floor. So there's force here and there's force here. In which direction do these forces act on the man? So a force acts between the man's hands and the box. Another force acts between man's feet and the box. In which direction does the... So this is going to be towards... Do these forces act? So the man is moving forward. So force on the man's feet. So the man is... It's going to be to the right. And on the hand is going to be to the left. So it's B. 12 should be B. Now let me explain that a little bit. So the man is pushing the box with his hand, so the man is applying with his hands a force forward. So the box is going to apply a force to the left, backwards, a reaction force, okay? So that is the red one's your answer. So let me do it right here so that you can connect that. So this here, if we talk about the foot of the man, see that the man is kind of pulling the floor back, right? So the foot is applying a force backwards. So what is the force on the foot? It's going to be opposite of that, which is to the right. If there's any confusion, please feel free to comment and let me know, and I'll try to just, make a video of all the confusions, like a compact video of just confusions. And also, tell me how the pace of the lessons is. If they're too fast or too slow, I'll modify it accordingly. In which situation is the resultant force equal to zero? A car turning a corner at constant speed? No. In the circle, turning a corner. Sorry, wait a second. Yeah, so in a circle, if a car is turning a corner is basically a part of the circle, right? So maybe this circle. So if a car is turning a corner, the force is going to be towards the center, so it's not equal to zero. So F net is towards the center. So A is not the right option. B, a rock falling freely on the moon. Again, not. Because the resultant force, if it's falling freely on the moon, there is still force of gravity of the moon, even though it's very, very little. The moon is going to attract the stone or rock a little bit. Not very strongly, a little bit. Free fall just means there's no air resistance, but there's still weight of the ball or rock. Okay? So there is a resultant force here. See a train going up a straight hill at a constant speed in a straight line. So this is your right option. Why? Because if you have a train, it's moving in a straight line first of all. So that means that its direction is constant and it's going at a constant speed. So the magnitude plus direction is not changing. That means the velocity is constant. And if the velocity of an object is constant, its acceleration is zero. Because what is acceleration? It's just change in velocity over time. If there's no change, then change in velocity is zero over time, then acceleration is just zero. So that, yeah, and if acceleration is zero from F equals ma, we know that if a is zero, then m multiplied by zero will definitely be just zero. So your net force is zero. I'm not even going to discuss D and I'm done. The satellite is orbiting the Earth. What's the direction of the force on the satellite causing the circular motion? It's always towards the center. So it's in the direction of motion of the satellite? No. It's away from the center of the Earth? No. It's towards the center of the Earth. The diagram, this is our last question. The diagram shows a block of stone on a rough horizontal surface. Force P acts on the block as shown. The block is at rest. A frictional force F acts on the block. Which row shows the direction of this direction size of F? Wait. I read the question way too fast for my brain to process it. Diagram shows a block of stone on a rough horizontal surface. Force P acts. Okay, block is at rest. Frictional force acts on the block. Okay, so there's a force P acting on the block, but the block isn't moving. So first of all, what's the direction of F? F is the friction force. It's always going to be opposite to the force that you're providing, so it's going to be to the left. P is to the right, so friction is going to be to the left. So it's either option A or C. Now, since the block isn't moving, that means your friction force is just enough or equal to the P. So the friction is like that. It's equal. And we know that when two forces, anti-parallel forces, are equal, your net force is zero, and the object is stationary, so F has to be equal to P, same as P. I mean, F cannot be more than P, because if F is more than P, that means the object just will move to the left. Friction can't move objects to the left or any direction, right? Friction, the maximum friction you can have is equal to the force that you're providing. It cannot be more than what you're providing. And the reason is that imagine you have a box, you slide it on a table, and it comes back to you. That would be ridiculous. The maximum that will happen is when you slide a box after a second or two, it's going to stop moving because your push was counteracted by the friction to stop it. Friction won't cause an object to move back. Okay? Alright, that is it for today, and if I rushed the lesson in the end, I'm so sorry. I will try to catch up in later lectures. All the best and good luck for your exams. Bye bye, take care. Happy studying.